Welcome to The Explainer, where we break down the big ideas shaping our world. Today, we are tackling one of the biggest questions imaginable. What is the ultimate fate of our universe? For more than 20 years, we really thought we had the answer. And honestly, it was a pretty lonely one, a story of endless expansion into darkness. But what if that whole story is wrong? To really get why this is such a huge deal, we first have to understand the story we thought we knew. A cosmic timeline that stretches out into an almost unimaginable blackness. I mean, the sheer scale of this timeline is just staggering. Based on the work of cosmologists like Fred Adams and Greg Laughlin, our current star-filled era, it's just a brief flicker of light. After that, you get trillions of years of stellar remnants, then an era where even black holes evaporate. And finally, nothing. Just a cold, dark, empty abyss we call heat death. And this grim forecast was all built on a Nobel Prize-winning discovery from back in 1998. The expansion of the universe isn't slowing down like we thought. It's actually speeding up. This acceleration, which we think is powered by a mysterious force called dark energy, became the bedrock of modern cosmology. It really seemed to seal our fate. But what if that bedrock is starting to crack? You see, in science, even the most established ideas have to stand up to new evidence. And very recently, two major new lines of evidence have popped up, forcing us to re-examine, well, everything. You know, as cosmologist Willem Elbers puts it, our data is just getting so precise now that we're starting to see these little hints that our standard model, it might not be the whole story. So let's dig into the two clues that are causing all this excitement. So the first crack comes from re-examining our main tool for measuring cosmic distances, these things called Type 1a supernova. The best way to think of them is as standard candles, because they all explode with a very consistent known brightness. We can figure out how far away they are just by seeing how dim they look. It's a pretty clever cosmic yardstick. Now, that 1998 discovery assumed that all these standard candles were basically identical. But a new study from a team led by Young-Wook Lee at Yonsei University is asking a really crucial question. What if they're not? What if the age of the star system actually changes the candle's flame? And what they found is pretty strong evidence that supernovae from younger star systems are just fainter than the ones from older systems. Now think about it. Because the distant universe was younger, we were mostly seeing these fainter explosions, and that made them look farther away than they really were, creating what might just be a cosmic mirage, the illusion of accelerating expansion. Okay, now for the second piece of evidence. This one comes from an amazing project called the Dark Energy Spectroscopic Instrument, or DESI. Instead of a standard candle, DESI uses a standard ruler. It's called baryon acoustic oscillations. Basically, these are giant frozen sound waves from the early universe that left a predictable pattern in how galaxies are all clumped together. So by measuring the size of this pattern at different distances, DESI has created the biggest, most precise 3D map of our cosmos ever made. Okay, so we got two totally independent clues. One from a fresh look at our standard candle, and another from this brand new high-precision standard ruler. And this is where it gets really, really interesting. Because they are both pointing to the exact same pretty radical conclusion. The standard model of cosmology, we call it Lambda-CDM, and that lambda part represents dark energy. It assumes this force is a constant, just baked into the fabric of space-time, always the same. But both of these new lines of evidence suggest something completely different, that dark energy is not constant. It's dynamic, and it actually appears to be getting weaker over time. And here's the absolute kicker. When the astronomers went back and corrected the original supernova data for that progenitor age bias we talked about, boom, it suddenly snapped into perfect alignment with the totally independent results from DESI's standard ruler. Two completely different methods now telling the exact same story. And that story is in extreme tension with the standard model. In physics, a 5 sigma result is the gold standard for a discovery. It means there's only a 1 in 3.5 million chance it's just a fluke. The tension between this new data and the idea of a constant dark energy is over 9 sigma. The odds of that happening by chance are so astronomical, it suggests something really fundamental in our understanding has to be wrong. So what does this all mean? I mean, if dark energy is indeed fading, it has absolutely monumental consequences for the ultimate fate of, well, everything. It means the end of the story might not be that long, cold, lonely heat death we've all been expecting. Instead, if dark energy continues to get weaker,
gravity could one day win the cosmic tug of war. It could halt the expansion completely and then begin to pull everything back together in a dramatic, universe-ending big crunch.
And as author Paul Gilster points out, this reopens the door to some really fascinating and, for a lot of people, more philosophically appealing ideas. A big crunch allows for the possibility of an oscillating cosmos, a universe that expands and contracts, maybe in a cycle, maybe forever. But let's be super clear here. This is not a closed case, not by a long shot. This is science happening in real time, a vibrant and active debate right at the very edge of what we know. Adam Rees, who was one of the original 1998 discoverers, he's still skeptical. And he points out, quite rightly, that it is incredibly difficult to be certain about the ages of stars at these vast distances. He argues the whole theory of an age bias rests on a pretty weak foundation.
But then others, like cosmologist Carlos Frank, are more cautiously intrigued. He admits it could be wrong, but he says the results are just too tantalizing, the conclusions too profound, to just ignore them. This debate is now front and center in cosmology.
So we're left with this really profound question. Has our universe pulled a cosmic U-turn, changing its destiny from a big freeze to a big crunch? Or are we just seeing a ghost in the data, some subtle error in our measurements that we haven't found yet? The next generation of telescopes and surveys, they'll have the final say. But for now, the fate of everything is once again up for debate.